Welcome back to another video. Here, we will talk about covariance and correlation. The joint probability distribution describes the likelihood or probability of two random variables, x and y, occurring together or coexisting at the same time. In other words, it gives the probability that x takes a specific value and y takes another specific value simultaneously. For example, if you roll two dice, one representing x, the outcome of the first die, and the other representing y, the outcome of the second die, the joint probability distribution would tell you the probability of both dice showing certain values at the same time, like x equaling 3 and y equaling 5. The sum of all possible joint probabilities in a joint distribution equals 1, as it encompasses all possible combinations of x and y in both discrete and continuous cases. We know that the expectation of x plus y, irrelevance to whether x and y are independent, always simplifies to the expectation of x plus the expectation of y. If we have weighted random variables, such as alpha x, then the expectation of alpha times x is the same as alpha times expectation of x. The two principles above combined can handle sums of weighted random variables. The expectation of alpha x plus beta y, where alpha and beta are constants, is given by alpha times expectation of x plus beta times expectation of y. This means you can scale or weight random variables, and the expectation respects those weights. This can be extended to handle sums of many weighted random variables. This property holds because the expectation is linear. Intuitively, the expectation is the average value of a random variable over its probability distribution, and adding or scaling random variables corresponds to summing or scaling their averages. If there are n random variables such as x1, x2, up to xn, the expectation of their scaled sum is the sum of their scaled expectations. This holds regardless of whether the variables are independent or dependent, because the expectation is a linear operator. In a more general setting, the expectation of scaled summation of two functions of x and y is the same as the sum of their scaled expectations. Finally, only for independent random variables, we can have that the expectation product of two independent random variables is the same as the products of their expectations. Linearity of variance simplifies the variance of alpha x plus beta y for independent x and y random variables to alpha squared variance of x plus beta squared variance of y. If x and y are not independent, the variance of scaled sum of x and y would need to count for their dependence through measuring their covariance. For dependent variables x and y, the variance of alpha x plus beta y is alpha squared variance of x plus beta squared variance of y plus 2 times alpha times beta times the covariance of x and y, and the variance of alpha x minus beta y is alpha squared variance of x plus beta squared variance of y minus 2 times alpha times beta times the covariance of x and y. Covariance is a way to measure the relationship between two random variables, like x and y. It tells us how changes in one variable are related to changes in the other. For example, if x increases and y tends to increase too, the covariance will be positive. If x increases and y tends to decrease, the covariance will be negative. If there's no clear relationship between x and y, the covariance will be close to 0. You can think of it as a number that summarizes how two things are connected. Covariance's notation is sigma of x, y, and can be calculated as the expectation of x minus mu, x, multiplied by y minus mu, y. The computational formula for calculating covariance is expectation of x, y minus the mu x multiplied by mu y. The units of covariance depend on the units of x and y. For instance, if x is measured in feet and y is measured in pounds, the covariance will have units of foot-pounds. This is because the covariance calculation involves multiplying the units of x and y. Unlike something like variance, which is always positive, covariance can take on any value between negative infinity and positive infinity. This range means that a large positive value shows a strong positive relationship. As one increases, so does the other. A large negative value shows a strong negative relationship. As one increases, the other decreases. A value close to 0 means there's no consistent relationship between x and y. Correlation is a measure of the strength and direction of the relationship between two random variables, like x and y. It builds on the concept of covariance, but is more standardized and easier to interpret. The correlation between x and y is denoted by rho of x and y. Key properties of correlation include 1. The sign of correlation matches covariance. If covariance is positive, correlation is also positive. And if covariance is negative, correlation is also negative. This is because the correlation simply takes the covariance and normalizes it.
2.
Correlation is a normalized version of covariance. It divides the covariance by the product of the standard deviations of x and y. This normalization ensures that the value of correlation of x and y always falls between -1 and 1, regardless of the units of x and y. A correlation score of 1 indicates a perfect positive linear relationship, while a correlation score of -1 indicates a perfect negative linear relationship. A correlation score of 0 indicates no linear relationship between x and y. 3. Unlike covariance, which has units like foot-pounds, correlation is dimensionless. This is because dividing by the standard deviations removes the units. This makes correlation a pure measure of relationship strength. While covariance tells us about the relationship between two variables, its value depends on the units of the variables, making it hard to compare across different contexts. Correlation solves this problem by standardizing the measure, giving a clear and consistent way to compare relationships between variables. Let's go over an example together. We are given a joint probability distribution, and we are tasked to show the covariance is 0. You can pause the video here and take a moment to answer this question. Using the computational formula, we need to find the expectation of x, mu x, expectation of y, mu y, and expectation of xy. In order to find the expectation of x, first, we need to find the marginal distribution of x, and second, find the integration of x times its marginal distribution over the domain of x. Here, we are combining these two steps by doing a double integration of x times the joint distribution. The inner integration, which is with respect to y, gives us the marginal distribution while the outer integration gives us the mean. We can find the expectation of y in a similar approach. Finally, we can find the expectation of xy by finding the double integration of x times y times their joint distribution. Plugging in these expectations within the computational formula, we can confirm that the covariance is 0. Thank you for listening to this short lecture on covariance and correlation.